So we're dealing with ideas from thermodynamics in class, and one way to think about thermodynamics is to think about the impact of temperature, volume, and pressure on different things. The easiest thing to look at is a gas, since those particles are very, very free to move. And so we're going to look at this in the light of the ideal gas law, thinking of how gas particles would move in a container, as long as that container's volume is allowed to change. So we have to imagine some cylinder This is going to be a cross-section of that cylinder, okay, with tons of gas particles on the inside, zipping around, free to move, whichever way they want to move, and with a piston that somebody could move in and out of that cylinder, or that the gas could move as well. Okay, so this is free to move inside of this cylinder which contains the gas. So pushing the piston in decreases the volume, pulling it out increases the volume. And so what is seen with regard to the behavior of the gas when certain situations arise? Well, we have the ideal gas law to describe that. So let me talk about that for a minute. The ideal gas law is PV equals nRT. So what does this mean? We have the pressure of the particles, we have their volume, the combination of those two things together equals the number of moles of the particles times the universal gas constant, R, times the temperature of the particles in Kelvin. This wouldn't work if temperature is in Celsius, because remember that there's a 0 and negative numbers in the Celsius scale, and so then you could have negative pressure and volume or 0 pressure and volume for a situation that actually has pressure and volume, so that makes no sense. So we have to keep temperature in terms of Kelvin. Okay. So what is the number of moles? The number of moles is the number of particles that would equal the same number of particles you get for 12 grams of carbon-12. It's based off of that. So Avogadro's number tells us that there are 6.02 times 10 to the 23rd particles per mole. So we have to think about that with regard to how to think about this situation with the number of moles. So the number of moles, N, is also equal to the total mass of whatever collection of stuff you're talking about. It could be paper clips, it could be balloons, it could be gas particles, divided by the molar mass of each particle. Okay? Total mass divided by the molar mass gives you the number of moles. So let's keep that in mind, but let's analyze this situation and see what happens. So if we hold the temperature constant, what is true about pressure and volume? If this side is a constant number, because the number of moles is constant, the R is constant, it's just a number, and the temperature is the temperature. So if we say that we're not allowing any gas particles to leave or enter our system, N is constant, and we keep T constant, what happens with P and V? P and V are inversely related. So if pressure times volume equals some number, if P goes up, V goes down. If V goes up, P goes down. And we can think about that in terms of what's happening here, that if you push the piston in, okay, the pressure of those gas particles are going to increase. What is pressure? Pressure is force per unit area. So it's the amount of force the gas molecules are exerting on the wall for whatever surface area they're hitting on the wall. So I'll talk about this in a little bit, but you can also think about the speeds of the particles and the kinetic energy of the particles. The higher the kinetic energy, the larger the force. If you squish this volume, they're going to collide with each other more, they're going to collide with the walls more, they're going to have a higher kinetic energy, which means that the pressure is going to be bigger. So as the volume goes down, the pressure goes up. And if you were to pull the piston out, and the volume increases a lot, the pressure is going to go down for the same sort of reason. Okay. So now what happens if you keep the volume constant and the number of particles? Then you have P here is proportional to T. So you have P times stuff equals stuff, well, other stuff, times T. So as T increases, the pressure increases. If T decreases, the pressure decreases. Which we can think about, too, again, if we think about temperature as the measure of the speeds of particles. Because we can think about the temperature as a measurement of the speeds of particles. So if the speeds of the particles goes down, because the temperature goes down, that means they're going to be hitting the walls of our container less. And so the pressure would decrease, because the force per unit area, the force the wall feels from the particles hitting it, goes down. Okay. So, also, what happens if we keep the pressure constant and then change the volume and temperature? We would have stuff times volume equals other stuff times temperature. So, if the temperature goes up, the volume has to go up in order for the pressure to stay the same. Again, thinking about the speeds of the particles and the energy they have, and therefore making them hit the wall with a certain force. If the temperature increases, in order for that force per unit area to stay the same, the volume has to get bigger, because the force is going to increase, therefore the area has to increase. So in order for that pressure to stay the same, which is force per area, the volume has to get bigger. If the temperature decreases, these particles are now sluggish in here. They're exerting less force on the walls of our container, and so in order to make that work out so you have the pressure being right, you have to decrease the area, since the force has decreased. Okay. So those are just relationships to think about with regard to this big equation here, which works for any ideal gas macroscopically. Okay? And another thing to note is that we don't have to write things in terms of the total mass divided by the molar mass. We can write things in terms of the number of particles. So the total mass here, so N is equal to the total mass divided by the molar mass, but the total mass would be the mass of each particle, like the mass of a paperclip times the number of paperclips, divided by the molar mass is the mass of a particle times the number of particles per mole. So that would be the mass times Avogadro's number. So small n is actually also equal to the number of particles divided by Avogadro's number. So let me put that back in here. We have PV is equal to N over NA times R times T. So I can take these two constants, because they're both just numbers, and I can make that into a new constant. So I have PV is equal to capital N times small k sub B times T. Where now this is the Boltzmann constant. Okay, and so this one, the universal gas constant, is in joules per mole Kelvin, and this one is just in joules per Kelvin. So you can look at the situation by looking at the number of moles you have, or you can look at it in terms of the total number of particles you have. Either way is a valid way of looking at it. You just have to know which one works best for what situation you want to look at.